Welcome back, everybody. In the last section, we were working on just kind of introductory concepts regarding probability. And in this section, we're going to start looking at a couple of specific rules for working with probabilities. So this section is on the addition and multiplication rules. We'll be treating the addition rule first because it's a little easier to deal with, and then multiplication rule later. So the first thing to do is to relook at what a compound event is. A compound event is basically an event that can be broken down into smaller events. Or said another way, it's an event combining two or more simple events. So an example would be rolling a die and flipping a coin. So we could look at whether the event of getting a 5 occurs and whether the coin comes up tails. The outcome of the die is one kind of simple event, and then the outcome for the coin, either heads or tails, would be another simple event. And we could look at various combinations of different outcomes of those two things. Okay, and so the first rule we have to work with is the addition rule, and it reads off like this. P stands for probability of for this chapter. So the probability of event A or B occurring is equal to the probability of event A occurring plus the probability of event B occurring minus the probability of event A and B occurring. So we're going to see an example that illustrates how this formula works. So we want to roll a die. We're going to find the probability that the number is odd or is divisible by 3. Okay, so the numbers that we could get are the numbers 1, 2, 3, 4, 5, and 6. So the probability that the number is odd or divisible by 3 is the probability that it's odd plus the probability that it's divisible by 3, and then both, minus the probability that it's odd and divisible by 3. Okay, so the probability that it's odd, okay, out of 6 numbers, there are 3 odds, 1, 3, and 5. Okay, so there's a 3/6 chance of getting an odd number. Okay, the number is divisible by 3. Out of 6 possible numbers, how many are divisible by 3? 3 and 6 are divisible by 3. So there's a 2/6 chance of getting a number divisible by 3. So now you'll notice when I highlighted those that the number 3 was highlighted twice, and that's because it meets both qualifications. It's both an odd number and is also divisible by 3. So we don't want to double count that, right? And so that's the reason for this last term, subtracting the probability of getting a number that is odd and is divisible by 3. The number that is odd and divisible by 3 is just that one number, 3. So we have 3/6 plus 2/6, that's 5/6, minus 1/6 is 4/6, and that, of course, reduces to 2/3. So overall, there is a 2/3 chance that we get a number that is odd or divisible by 3. Okay, a second way to look at that kind of overlap idea is through the use of a Venn diagram. Depending on where and when you went to school, these were a thing for describing sets of numbers or sets of other things. If we have 2 sets, A and B, we could consider the subsets that they may have in common. That would be the overlap between the 2 sets. We could consider the part or the elements that are just in A alone, or are in B alone, or in neither. So when we're looking at A or B, that would be all the elements in set A. And then for set B, if we want the elements of set B also, you can see that there's overlap there. And that's why we ended up subtracting that bit of overlap, because we don't want it to be counted twice. Okay, all right, here's another example. Suppose that you work for a company and you're doing a survey of some sort involving employees, and You've got this records of full-time status and then whether they are female or not. And so these are the results. There are 25 female full-time employees, 20 male full-time employees for a total of 45 full-time employees. Ones who are not full-time, there are 28 not full-time females, 27 not full-time males, 55 not full-time total. And then the total column on the right would be there's 53 total females, 47 total males, and 100 total people. So make sure that you can read this table, okay, because we're going to be using it, tables like this for at least a little while. So in columns, we have full-time, not full-time, and then total. In rows, we have female, then male, and then total. Okay, we want to find the probability that a randomly chosen employee is female or is full-time. Okay, so let's try. Female or full-time, that would be the probability. I'm going to use F for female or FT for full-time. That will be the probability of getting a female employee plus the probability of getting a full-time employee minus the probability of getting a female and full-time employee. Okay, so let's see. Out of the 100 employees there are how many females? There are 53 total females. And then out of the 100 employees, how many are full-time? There are 45 full-time employees. Okay, so the thing is right here, if we just stopped right here and say, okay, let's just add together these two probabilities. The issue is the 53 out of 100, those 53 females here and 45 full-time employees here, we've counted the 25 full-time females twice. We counted them for being female and we counted them for being full-time. So they are double counted. And that's the reason why we have to end up subtracting in this next part. Out of the 100 employees, how many are female and full-time? That was 25 that are female and full-time. Okay, so then that's 83 or 73 out of 100. Yeah, looks right. Okay, or 0.73 if you like decimals. Okay. All right, moving on. Definitions. We want to know what it means for two events to be disjoint or mutually exclusive. Two events are disjoint or mutually exclusive if they can't occur at the same time. For example, let's say you flip a coin. E is the event you get tails, and F is the event that you get heads. If the coin comes out tails, it's not heads. If it's heads, it's not tails. You can't have both occurring at the same time. Okay, roll a die. You get a 5. That's event E. Event F is you get an even number. Is it possible to get an even number that is a 5? No. Is it possible to get a 5 and also get an even number within one roll? It's not possible. Okay, so those are mutually exclusive or disjoint events. Going back to our employees, is it possible to get a female employee who is simultaneously full-time and not full-time? Well, she's either full-time or she isn't. Okay, it can't be both. Okay, so that would be mutually exclusive or disjoint. Okay, if you have two events that are mutually exclusive, the probability of A and B is 0. Remember, we had discussed last time how all probabilities fall along that scale from 0 to 1, where 0 is events that never happen, and 1 was for the probability of events that definitely will happen. So if A and B can't occur jointly, then the probability of both occurring has to be 0. Okay, and so that makes our OR formula simpler. The probability of A or B is then just the probability of A plus the probability of B. And that is because when that happens, this probability of A and B is equal to 0. So all that's left is the probability of A plus the probability of B. Okay, so a couple of examples. Let's say we roll a die. We want to find the probability that the number is even or is less than 5. So the probability of getting a number even or less than 5. Okay, so that would be the probability of getting an even number. Let me actually write it out. Plus the probability of getting a number that is less than 5. Is it possible to have an even number that is less than 5 when you roll a die? Yeah, those are not mutually exclusive. So we could say probability even and less than 5. Okay, so the probability of getting an even number, there are 3 out of 6 numbers that are even. Numbers less than 5, that's 1, 2, 3, and 4. So there are 4/6 that are even, or sorry, that are less than 5. And then evens that are less than 5. Well, the ones that are less than 5 are 1, 2, 3, and 4. The ones that are also even, there are 2 of those. Okay, so this would give us 5/6. Okay, notice that if I forgot, okay, if I forgot that, if I wasn't paying attention, if I didn't bother watching the last video, if I just stopped and said, okay, well, this is 3/6 plus 4/6, that's 7/6, right? But we know that probabilities all lie on the interval between 0 and 1, so you can't have a probability that's 7/6. So that would tell me that something is wrong, and I'd better go back and fix it. And sure enough, we're missing that last 2/6. So in all, we have 5/6 for our probability. Okay, try one more. Pick a letter of the alphabet. We want to find the probability that the letter is a vowel or is in the set W, X, Y, and Z. Okay, so here let's say that W is not, or Y is not a vowel. Okay, so these are two mutually exclusive events. If you get a letter in this set, it's not a vowel. If you get a vowel, it's not in this set. So it's going to be a probability of getting a vowel plus the probability of getting W, X, Y, or Z. Okay, so I don't have any minus on this one because the probability of both events occurring is 0. Okay, there's a 5/26 chance of getting a vowel and then a 4/26 chance of getting W, X, Y, or Z. So that is 9/26. Okay, by the way, when you go to do this work, pay attention to the directions if you're supposed to give the answer as a decimal or as a fraction. If you give it as a decimal, are you supposed to round it to some number of decimal places, right? So make sure to pay attention to those directions. Okay, for our next couple of examples, we'll be using decks of cards. And some people have more or less experience with this, so I wanted to go over it with you. First, so a deck of playing cards consists of 52 cards. If you already know all about this, skip ahead, okay? A deck of playing cards consists of 52 cards. They're organized into 4 groups called suits, just like a suit of clothes. They're organized into 4 suits. The uppermost one here is clubs, then diamonds, hearts, and then finally spades. Out of the 4 suits, 2 are black and 2 are red. Clubs, diamonds, hearts, and spades. Within each suit, the cards are further divided into ranks. And there's A or ace, and then 2 through 10, and then a jack, queen, and king. So the ace sometimes counts as 1, sometimes counts as 10, sometimes counts as some other number of points, depending on what kind of game you play. Okay, we're going to just call it ace for this. That's all we need. Okay, so we have aces 2 through 10, and then jack, queen, and king within each rank. So there are 52 total cards. They're divided into 4 groups. 52 divided by 4 is 13. There's 13 cards in each rank. 2 through 10 plus the ace, if the ace, especially if it's counting as 1, there's 10 cards. And then the jack, queen, and king make 3 more, so a total of 13. The jack, queen, and king are also called face cards. because each card has a face on it. Okay, sometimes people will ask me if an ace is a face card. Okay, you tell me. Okay, the face cards are jacks, queens, and kings. All right. So that has been a quick look at a deck of cards. If you are not so familiar with this, you may want to get like a Google image or a deck of cards or something so that you could look at it as you answer some of the questions. Okay. And if you have questions for me about this, let me know. All right. So let's say then that we draw a card from a deck of cards. Like our coins are always fair and our dice are always fair, you can assume that our decks of cards are always well shuffled, okay? So that any one card is equally likely to be drawn as any other. Okay, so let's say we want to know the probability that a black card is drawn. Well, there are 52 cards, out of which 26 are black. Or if you look at the picture, half of them are black and half are red. And sure enough, 26 out of 52 is a half. Okay, the probability of getting a card that is hearts, there are 52 cards, out of which 13 are hearts, which is the same as 1/4. There are 4 different ranks. One of the ranks, those 13 cards in the third row, are all hearts. Okay. All right, so now more interesting, we want to know the probability of getting a card that is hearts or a face card. So this would be the probability of getting hearts plus the probability of getting a face card minus the probability of getting face card and hearts. Okay, so the probability of getting hearts, we know that that's 1/4, but I'm going to leave it in terms of 50 seconds now to make the fractions easier. So hearts, there are 13 out of 52. Face cards, picture. There's 4 suits and 3 face cards in each suit. 4 times 3 is 12. There are 12 total face cards. So 12 out of 52 are face cards. And then we want to know the probability of getting a card that is a face card of hearts. And there are 3 of those. Okay, so we have 25 minus 3, or 22 out of 52, which is 11/26. All right, so once again, just to make sure that we are okay with that, we want to know the probability of getting hearts. That's all these. Or a face card. That's all those. And then as you can see, there are 3 cards that are hearts and face cards. So we don't want to count those among the hearts and face cards twice, which is why we ended up subtracting that 3 out of 52 there at the end. We had 13 heart cards, 12 face cards, and 3 cards that are both hearts and face cards. And so we had to subtract for that duplication. Okay, one more. We want to know, we picked a card, we want to know the probability that it is a 7 or a face card. Okay, so think about that. We're going to add the probability that it's a 7 and the probability that it's a face card. We don't have to do any subtraction this time because the 7s, do any of the 7s have faces on? No, 7s are not face cards. So they're disjoint events, and so we don't have to worry about any kind of subtraction. All right, so 7s, there are 4 7s in a deck of 52 cards. And then there are, again, 12 face cards in a deck of 52 cards. That's 16 out of 52, which simplifies to 4/13. You divide out that common factor of 4. Okay, all right, so that takes us to the end of that example. All right, so that'll actually take us to the end of this first part on section 4.2 involving the addition rule. In our next video, we're going to go on to the multiplication rule. Okay, in the meantime, let me know if you have any questions and have a great day.